let's move into our continuing conversation about pH. So we ended last lecture talking about the pH scale and kind of the nature of the scale itself as a logarithmic scale, being able to look at it and say, okay, this means that it's this many more times acidic or this many more times basic. But where do we actually get those concentrations? How did we come up with the idea that at a neutral pH of 7, the concentration of hydronium is 10 to the negative 7th molar? Well, this comes from something called the autoionization of water. And how this works is, if you remember back to Monday, we talked about the idea of water being amphiprotic, meaning that it can act as an acid or as a base, just depending upon what is around. Well, by that logic, it can also act as an acid or a base to itself. And so if two water molecules react with each other, one acting as an acid and the other as a base, then what we would end up getting is a splitting of water into the hydronium ion and the hydroxide ion. Now, in this reaction, notice that we are dealing with that double-headed arrow here, which indicates that this is a reversible reaction. And this kind of thing is not a one-way street. So we know that the majority of this reaction is actually going to be in this direction here, and that only small quantities of ions will be present relative to the amount of water that does not ionize. But based upon this idea, we know that regardless of any kind of interaction with acid or base, there will always be, because of the autoionization of water, there will always be hydronium and hydroxide present in the solution at any given time. If that solution happens to be neutral, that means that the hydronium and the hydroxide concentrations are equal to each other, and they basically level each other out. That concentration is at 1.0 times 10 to the negative 7th molar. So again, if this is the concentration, 1 times 10 to the negative 7th, that means that I have 1 times 10 to the negative 7th molar hydroxide, 1 times 10 to the negative 7th molar hydronium, and relative to the amount of water, water's concentration in itself is about 56 molar. We're talking about a massive difference in scale. 56 compared to 0.1 millionth represents about a 560 million time difference in concentration. There are far, far more molecules than there are ions in any water-based solution. So there are some things that we can conclude. First of all, if the hydronium and hydroxide concentrations are set in that way and are equal to each other, then what we get is that their product, concentration of hydronium multiplied by the concentration of hydroxide, gives us a value called Kw. Value of Kw is 1.0 times 10 to the negative 14th. And that comes from the multiplication of 1 times 10 to the negative 7th multiplied by 1 times 10 to the negative 7th. So regardless of situation, we're always going to get the same value when I multiply those two concentrations by each other. Again, there will always be some hydronium and some hydroxide present in the solution, regardless of what else is in the water. But what we can say definitively is that when we have an acid, that acid is going to come about because we have more hydronium than we did hydroxide. And that higher concentration of hydronium is going to kind of tip the scales toward a lower pH, a pH that is less than 7. And in base, we're going to have a higher concentration of hydroxide, and that's going to tip those scales in the favor of the hydroxide and get it to a higher pH, a pH greater than 7. Because again, pH is equal to the opposite of the logarithm of the hydronium concentration. So when the concentration of hydronium is high, we're going to see lower pHs come out as a result. When the concentration of hydronium is low, because we've got more hydroxide in there, then the pH is going to be on the higher side. All right, questions so far with this? So just to kind of reiterate, our Kw, our constant for water, is equal to the concentration of hydronium multiplied by the concentration of hydroxide. And this will always equal 1 times 10 to the negative 14th. It is a constant value. That's what the K there is for. We use the designation K for constants in a lot of different applications. Again, just to reiterate what those mathematical equations here at the bottom were saying, in acidic solution, we've got extra hydronium, which means the hydroxide concentration is going to be low. These are on, we can think of it as kind of like a teeter-totter. I've got hydronium on one side and hydroxide on the other. When it is neutral and the two are equal to each other, we're going to have a pH that is pretty close to 7. If the scales tip, in favor of the hydronium, where we've got large quantities of hydronium and lower quantities of hydroxide, we will see that the pHs end up being less than 7. We call that solution acidic. If the scale tips the other way, then our pH goes up. And we call that solution basic. All right, so in summary, what does this look like in terms of number values? Again, for neutral solutions where pH is equal to 7, we see even concentrations of hydronium and hydroxide. In acidic solutions where pH is less than 7, we see a higher concentration of hydronium, a lower concentration of hydroxide. In basic solutions where pH is greater than 7, we see a lower concentration of hydronium, a greater concentration of hydroxide. But notice that in all three cases, my Kw value is constant, doesn't change. Now, this is the kind of information that we can really use to our advantage if we know a little bit about a solution that we are measuring. So in the lab, we've dealt in very, very simple kinds of calculations. If I have a concentration of 10 to the negative 10th, then the concentration of the other was 10 to the negative 4th. My exponents had to equal up to negative 14. But with these kind of values in play, we can actually do calculations that are a little bit more complicated. So for example, if I know the hydronium concentration, I can figure out the hydroxide concentration by taking that hydronium concentration and dividing it into 1 times 10 to the negative 14th. And if I know the hydroxide concentration, I can do the exact same thing. Kw divided by the hydroxide concentration would give me the hydronium concentration. And again, we did these kinds of calculations in lab, but we did them with very simple numbers. The hydronium concentration was 10 to the negative 4th, which meant that the hydroxide concentration was 10 to the negative 10th. All we did was, since the values were 1 over 1, we could just subtract the exponents from each other. The exponents had to equal up to 14. And so these were the kinds of examples that we did in lab, where if I knew the value of one, I could easily find the value of the other, because since my values all were 1 times 10 to the exponent, 1 times 10 to the negative 14th over 1 times 10 to the negative 5th, my 1's cancel out. 10 to the negative 14th over 10 to the negative 5th would give us 10 to the negative 9th. Do the same kinds of things over and over. And what you end up finding is that in these simple examples, all I have to make sure is that my exponents add up to negative 14. So this would be 10 to the negative 8th. This would be 10 to the negative 2nd. But what if we aren't given simple examples like these? What if we're given data that isn't just simply 1 times 10 to the negative something. How do we work with that? How do we rationalize that? Well, we can use the same kind of equation, only slightly different in terms of the numbering. So the equation that we use for an example like this would be the same. The concentration of hydronium is equal to 1 times 10 to the negative 14th over 1.9 times 10 to the negative 8th. Remember that on your calculator, when we're dealing with scientific notation, we need to utilize our exponent button. If you have a Casio, that exponent button looks like this. It's the EXP button. If you have a TI calculator like this one, the exponent button is going to be like this. It's going to look like this. It's an EE. Remember, that button replaces your scientific notation. So if I want to input 1 times 10 to the negative 14th, I would put in 1.0 E negative 14. Same thing on the Casio, 1.0 exponent negative 14. That's how I input my scientific notation. Now the value here was 1.9 times 10 to the negative 8th, right? So I'm going to divide by 1.9 E negative 8, enter. Divide by 1.9 E negative 8, enter. Both calculators give you the same thing, 5.3 times 10 to the negative 7th. On the TI, since it had enough decimal places here, you'd have to count that out. But it's 1, 2, 3, 4, 5, 6, 7 spots away. So my hydronium concentration was 1 times 10 to the negative 14th divided by 1.9 times 10 to the negative 8th, which we just calculated 5.3 times 10 to the negative 7th molar. So when my numbers are not nice and clean, I can still use the same equation to figure out my concentrations. Is this acidic, basic, or neutral? Well, there's two ways to look at it. One, I can compare 1.9 times 10 to the negative 8th molar versus 5.3 times 10 to the negative 7th molar. Which one of these is bigger? I've got a smaller exponent here. So that's the bigger value. So I've got more hydronium than I do hydroxide. which means that this is an acid. Now, the other way I could have done this is I could have calculated the pH. pH is equal to the negative log of the hydronium concentration, which would be the negative log of 5.3 times 10 to the negative 7th. On most of your calculators, the button you would hit there is, if you have that concentration in there, 5.3 times 10 to the negative 7th, and you hit that logarithm button, it would give you negative 6.28, which if I take the opposite of that, gives me a positive 6.28. So the pH here is positive 6.28. That is slightly below 7, so we could also determine that it's an acid based off of its pH as well. pH is less than 7. So we could conclude it's acidic there as well. Right. Let me just throw that up on the calculator here, just so you can see. If you're dealing with a scientific calculator like this one, where you've got to press the functions individually, I've got my 5.3 times 10 to the negative 7th. If I touch the logarithm button, it would give me negative 6.27. Remember that for pH, I need to take the opposite, so I need to hit my plus minus button, and that turns that into positive 6.28. On the Casio, pretty much the same operation. 5.3 times 10 to the negative 7th. I hit the log button, and then I hit the negative button. General rule of thumb as far as significant figures are concerned, the number of sig figs that goes into a calculation becomes the number of decimal places in the pH. So I had two significant figures, 5.3 times 10 to the negative 7th. That became two decimal places. That's why we recorded this as 6.28 instead of just 6.3. All right, let's try another one. The hydroxide ion concentration in a soil sample was determined to be 5 times 10 to the negative 7th molar. What is the pH of the soil, and is it acidic or basic? Now, there are two approaches that we can take to this problem. One of the approaches would be to turn this hydroxide concentration into a hydronium concentration, and then turn that into a pH. That would be one approach. The other approach would be to turn this pH into what we would call the pOH, and then turn the pOH into pH. Now, we haven't talked about pOH yet, but, excuse me, it's cut from the same cloth as what we just did with hydronium. pOH is equal to the negative log of the hydroxide concentration. And that's all well and good, but if you can't convert the pOH into pH, it's not that useful. Well, the other half of this is that pH and pOH add together to give us 14. So what I can do, the alternative method here, is if I take the logarithm of this value, that would give me the pOH, and then I can subtract that value from 14. Since algebraically speaking, the pH of the solution is equal to 14 minus the pOH of the solution. And to me, that's a little bit easier. Because this step requires multiplication and division. This step requires a logarithm. Whereas the purple line, yes, I've got to do a logarithm here, but then I have to do a subtraction. And if I'm going to compare doing a subtraction versus doing a multiplication from an algebraic standpoint, I'll take subtraction every time. It's a lot easier. It's a lot less likely to make mistakes. I'm going to go that direction. So my first step here is to find the pOH, which is equal to the opposite of the log of 5.0 times 10 to the negative 7th. So put that into my calculator, 5 times 10 to the negative 7th, the logarithm, I get the opposite of negative 6.30. Negative of a negative is positive, so my pOH is 6.30. Since the pH is equal to 14 minus the pOH, 14 minus 6.30, I'll get a value here of 7.70. Like I said, subtraction is always easier than multiplication. Addition and subtraction, sometimes you can do it in your head. The numbers are easy enough to work with. Multiplication and division, you almost always need a calculator. And especially with scientific notation, there's a lot more times where you can make mistakes inputting the wrong values in your scientific notation. With a pH of 7.70, is this an acidic solution or a basic solution? Basic. Anything over 7, we're going to consider basic. So this soil is slightly basic, which, depending on what you're trying to do with the soil, may not necessarily be a bad thing. All right, questions with this example? Okay, before I set you loose on this one, what I want you to do for each of them is we have to take these concentrations and turn them either into H plus or hydronium concentrations or hydroxide concentrations. Once you do that, then you'll be able to determine the pH because you'll know what the H plus or the OH minus concentration is. So in the case of this first one, I have exactly one hydrogen ion for every HCl molecule. So in that case, my concentration is going to be the same as my H plus. Which means I can take the pH of it directly, the negative log of 0.00085, which would give us a pH of 3.07. Question we would ask ourselves is, does this make sense? Well, we're dealing with hydrochloric acid. It's an acid. Not only is it an acid, it's a strong acid. And even though the concentration is relatively low, a strong acid is going to have a pretty acidic pH, and 3 is definitely going to fall into that category. All right, try the other two on your own here. See where it gets you. And I'll come around and kind of see how we're doing, and then share the answers, and we will call it a week from there. Let's go through the answers here since we're just about out of time. I think where we're kind of struggling is, what do we do with the numbers? So in the case of number 2, we had 0.01 molar sodium hydroxide. I have to recognize that I get 1 hydroxide out of this for every molecule. What that means is that the concentration here would be the same as the concentration of the hydroxide. The only time that's not going to happen is if I have like a diprotic acid or something like calcium hydroxide that has 2 hydroxides per. Then I would have to multiply the concentration by however many hydrogen ions or however many hydroxide ions. But I've got a hydroxide concentration here, 0.01. I can turn that into a pOH by taking the logarithm of that, and I would get a pOH of 2.0 as a result. And again, since this came from hydroxide, this is the pOH, not the pH, which means I need to subtract it from 14 to get the pH. And so the pOH was 2, the pH is 12. Again, this is where that check your answer to make sure it makes sense business comes in. If I record a pH of 2, that would indicate a pretty strong acid solution. Well, this is sodium hydroxide, which we know to be a base. So we'd expect it to have a pretty strong base pH. So if I come up with 2 for a pH of a base, I know I've made a mistake somewhere. Most likely mistake is that I'm interpreting pOH as pH, and I need to subtract from 14. In the case of number 3, again, I've got a 1-to-1 ratio, so my concentration of acid is also the concentration of the hydronium. And so to find the pH, I just take the logarithm of that. The log of 1 is 0, so I've got a pH of 0 in this case, which would indicate a really strong acid, which nitric acid is strong and it's also concentrated, so the pH there makes a good bit of sense. So we're going to do a couple more examples on Monday just to kind of close this out. If you thumb through some of the slides that kind of follow this one, you'll see that a lot of the information that I've given you already is kind of in there also, just kind of looking at it. We already talked about pOH. We already talked about the relationship between pH and pOH. So we'll start from here on Monday talking about how do I get concentrations out of pHs. Have a good weekend.